Welcome to this presentation on execution-guided line-by-line code generation, or EG-CFG. This is a joint work by Boaz Lavon, Shahar Katz, and Lior Wolf from Tel Aviv University. Large language models can generate code with impressive fluency, but they do so based only on static text patterns. They don't understand how the code actually runs, so even if it looks correct, it often fails when executed. To address this, many recent methods rely on iterative refinement or multi-agent workflows. They generate entire blocks of code, test them, and use the feedback to revise or debug. But these methods operate in discrete cycles. They wait until a full program is written before reacting. And they rely on explicit supervision, such as pass-fail signals or handcrafted critiques. In contrast, our method, EG-CFG, takes a more human-like approach and builds solutions one line at a time. After each line, the model pauses and executes, just like a developer might run their script to see what happens. This step-by-step reasoning supports exploration of different possibilities as the solution evolves, observing how the program behaves as it's being written, rather than waiting until the end. The key to this approach is the feedback signal. Instead of relying on pass-fail outcomes or predefined rules, we let the model observe how its code behaves through execution traces. These traces are structured logs that show what happened when the code ran. They include things like which lines of code were executed, the values and types of variables, function return values, and any errors or exceptions that occurred. This gives the model a rich, step-by-step view of the program's behavior, not just whether it worked, but how it worked or why it failed. So how does this feedback guide the model? After each line, we sample several possible continuations using beam search. We then run these candidates, collect their feedback, and aggregate everything into a single dynamic signal, which we inject into the prompt. Now, the model sees not just the code it has written, but also how future possibilities behave. We then use classifier-free guidance to blend the model's vanilla predictions with ones shaped by this execution feedback. From this blended distribution, we sample the next line token by token. Traditional methods can't fully leverage parallelism because their logic depends on sequential refinement, where each cycle must wait for the previous one to finish. In contrast, EG-CFG was designed for parallelism by default, enabling faster, deeper, and more scalable exploration. It employs a multi-agent approach built from a single model and a shared prompt. Each agent works on the same task, but with a different configuration, such as sampling temperature or how far ahead to look. This allows them to explore diverse reasoning paths, all in parallel. On the MBPP benchmark, EG-CFG achieves 96.6% accuracy, setting a new state-of-the-art, and doing so with an open-source model. That's a major leap over previous methods, including those using GPT-4. It also performs exceptionally well on MBPPT, a tougher variant with extended and more challenging test cases, reaching 73%, far ahead of all baselines. On human eval, EG-CFG reaches 96.95% accuracy, positioning it among the top-performing systems. Remarkably, on human eval ET, which pushes models with deeper and more diverse test cases, it sets a new record at 87.19% accuracy. The success of EG-CFG on the ET versions demonstrates that the obtained code is robust and holds up under pressure, even in the most complex testing scenarios. On the challenging code contest benchmark, EG-CFG achieves a new state-of-the-art with 58.18% accuracy, outperforming leading GPT-4-based methods, demonstrating its effectiveness even on competition-level complex programming tasks. Thank you for listening.